So welcome to our part 2 of our top 40 2018 IECC requirements that you should know. We're going to be covering commercial HVAC and residential today. Joining me is Ryan Siegel from our office. We're both members of the Smart Energy Design Assistance Center. If you have questions during the presentation, if you would use the Q&A window, we'll be sure to catch those questions. Sometimes ones entered in chat get lost in the chat window. So if you want to make sure we answer your question, please enter those into the question and answer section. And I will turn it over to Ryan to get us started.
Well, thank you, Sean, and good afternoon, everyone. We're here from the Smart Energy Design Assistance Center housed at the University of Illinois. I just want to provide a few notes. Today's presentation is being recorded and will be archived along with a PDF of today's presentation at our website, SEDAC.org. Also, everyone will receive a certificate of participation for today's presentation. If you are ICC or AIA members and would like the continuing education credits for those, when you receive your certificate of participation, please go ahead and reply back to us with your ICC or AIA number, and we will go ahead and file those for you. We will note the system has been a little slow as far as updating those, so it may take a few days for that to show up in your online information. So today we are going to cover some of the changes from the 2015 going up to the 2018 International Energy Conservation Code, which is now the basis of the Illinois Energy Conservation Code. As Sean noted, we're going to talk today particularly focusing on commercial HVAC and residential provisions. So we're going to talk about 20 of those, and also wanting to make sure that people understand how to comply with the present Illinois Energy Conservation Code. So, as I noted, we are housed at the University of Illinois at Urbana-Champaign. We are also part of a public-private partnership in coordination with the 360 Energy Group out of Chicago. And our primary mission is to reduce the energy footprint across the state of Illinois, both public and private sector. And this energy code training is part of how we look to accomplish that mission. We will note that today's training, along with all of the Energy Conservation Code programs that we have at the Smart Energy Design Assistance Center, or SEDAC, is provided in part by the Illinois State Energy Office housed at the Illinois Environmental Protection Agency. So I do want to thank them for providing some support for that. For all projects across the state of Illinois and people involved with projects here in the state, we do have technical support available. So that could be building owners, occupants, design professionals, and code officials. So if you do have questions, feel free to reach out to us after this presentation through our email, energycode@sedac.org, or we do have an 800 number. We do have several online resources available at our website, sedac.org/energy-code. Some of those include archived versions of our previous workshops and webinars, as well as several online on-demand training modules. These training modules take approximately an hour to an hour and a half to complete, and they're presently written as more of introductory information. So may be beneficial for those that may be a little less familiar with code as we move forward. Also, we do have several helpful links there, which I'll talk a little bit more about here in a little bit. So with that, the Illinois Energy Conservation Code changed versions from the 2015, moving up to the 2018 International Energy Conservation Code for permits that were applied for here in the state of Illinois. starting July 1st of last year, 2019. City of Chicago moved ahead a little bit earlier. They moved beginning with permits applied for starting with June 1st of 2019. So this is now moving forward in the 2018 version. One of the big changes that we had with this cycle is for state-funded facilities. Commonly, these were for state colleges and universities, along with other state-funded facilities. Previously, they were required to use ASHRAE 90.1. This has been changed in the current version. They now have the same options as the rest of the state, showing compliance through either ASHRAE 90.1 or the International Energy Conservation Code. So for those that deal with state-funded facilities, that gives a little more flexibility going forward. We do like to call out best practices when we see this. This is one such best practice that we have found as far as assisting projects with code compliance, and that is for through the City of Chicago and their building department. They have provided this compliance statement that projects, along with their permit application, can go ahead and provide this with the submittal, which provides some information to the plan reviewer as far as what they are expecting in the document. You'll see towards the lower end of the page there, you can check what compliance method. So if someone checks the COM check box, then the plan reviewer knows that they're going to be looking for that COM check report and not necessarily the energy cost model documentation. Or similarly, if someone checks the energy cost budget, they know to be looking for that, but not the COM check report. So that can be very useful for plan review. One thing that we would ask as we move into our new program year coming up is for design professionals and code officials, if there is certain documentation and tools that would be beneficial, such as a compliance statement, such as shown on the screen, please go ahead and let us know what some of those materials may be helpful to you, and so we can look to develop some of those tools for compliance across the state of Illinois. As far as access to the International Energy Conservation Code, along with the Illinois and Chicago amendments to that, rather than trying to furiously write down these links, these are linked directly from our website, so you can go ahead and go through our website under the helpful links and find the links to each of these. We do call out that the International Code Council has done a very good job as far as their search and find function. So their online versions are very easy to navigate and find what you're looking for. The ASHRAE 90.1 documentation is a little bit harder to search through. So we would encourage, if you do have questions or need some printouts or documentation of the code, go ahead and go through the ICC's website for. We have done several previous webinars here this current program year, and we do have one coming up next Wednesday, which is looking at ComCheck and ResCheck, a walkthrough. So if you are interested in looking for some more education and information on that, we would encourage you to go ahead and register for those. So with that, I'm going to turn it over to Sean to talk about the commercial HVAC section.
All right, thank you, Ryan. So just a quick summary of the topics we're going to be covering for commercial HVAC: energy recovery systems, equipment sizing, fault detection and diagnostics for economizers. We're going to focus on system commissioning documentation, what's required there, shut-off dampers, making sure those get adequate seals, duct sealing and construction, insulation, demand control ventilation, protection of piping insulation, domestic water heating circulation systems, and freeze protection controls. And then Ryan will be covering the residential section. We'll come back to that list in a minute. So moving on to energy recovery ventilation systems. This is a mandatory provision in the code. There are 2 tables in the code. We've condensed them down on this slide into one table. But based on hours of operation of the fan system and the percent of design outside air at the full design airflow rate for the fan unit, these will determine where your requirement for energy recovery is. Energy recovery devices have to be able to recover 50% of the enthalpy difference between inside and your exhaust air streams. And kind of an important component here is that they have to have a bypass ability so that you can bypass your energy recovery device in order to economize properly. There's nothing worse than trying to bring in free outside air cooling and your recovery device is heating that air up and you're forced to do mechanical cooling on it. So having that bypass capability is an important component of that. For energy wheels, there's 2 ways that can be done. You can have bypass dampers around the energy wheel. We see that most frequently just to limit pressure drop, but you could also just stop the wheel's rotation, and that qualifies as bypassing. And there's a significant energy reduction potential for buildings that use energy recovery ventilation systems. The Energy Code does list exceptions to where ERVs cannot be installed. Most of these are based on some kind of hazardous fume in the exhaust stream. And the reason that ERVs can't be used in these is that most of them have some carryover of the exhaust stream into the fresh air stream. If you've got hazardous fumes, odors, smoke exhaust, grease, you don't want to carry that over and blow it back into the building. However, we would like to note that even though certain systems don't have to have or can't have ERVs installed, they can have heat recovery devices installed instead. I know a lot of laboratory buildings, those exhaust systems will have energy recovery loops, runaround loops that just exchange heat with the air instead of heat and humidity. It's a great way to reduce energy usage in those buildings. And so it's a good way to help reduce overall operating costs for your clients. So again, even though there are certain areas with hazardous exhaust fumes where Energy Code per reference to the International Mechanical Code will not allow energy recovery devices to be installed, you can still use heat recovery devices. So we just like to call that out. This is the list of those exceptions, and mostly they are restating the exceptions that are in the International Mechanical Code. There are some additional ones, so where you've got VAV systems that reduce airflow for lab hoods, makeup air to a certain extent, and have semi-conditioned air coming into those that isn't less than 2 degrees warmer or less than 3 cooler than the room temperature. Spaces without heating or cooling beyond 60 degrees Fahrenheit. So that's the list of exceptions from the International Energy Conservation Code. Moving on to equipment sizing. The Energy Code specifies that output capacity for heating and cooling equipment should not exceed that of the smallest available unit that will meet the heating and cooling loads for the building. The code does allow for N+1, so you can have standby equipment installed. And it also allows units with capacity controls inherent in their control systems to be installed with a greater capacity than load, as long as that control system then backs those systems off to match the load of the building. One really good example of this are modular boilers and modular chiller systems. They have those controls built into them, and having those also provides some redundancy for your clients. Ways to do sizing testing. ASHRAE ACA has a standard for determining loads for buildings, and there are a large number of modeling programs out there. eQuest and Energy Plus are very popular ones. Carrier has the HAP program. Trace has their proprietary tracer program. So there are a number of ways to do those load calculations and equipment sizing that are compliant with the code. Some of the issues we see, usually with oversizing of units, not so much with undersizing. But you've got unnecessary increased capital costs for the client if you oversize that equipment, because you're paying for a lot more material and product to be there that won't necessarily be used. And continual part load operation of that equipment is detrimental to its service life and its overall energy efficiency. So right sizing of equipment has important short-term energy consumption implications and long-term equipment life cost considerations. Looking at Economizer fault detection and diagnostics, this is important because it was part of the 2015 IECC, but the 2018 IECC's language updated to make this a requirement instead of just a capability for the system. Fault detection diagnostics have to be able to monitor various temperatures, supply, outside air, return temperatures coming into the system, provide key status points, whether the economizer is active or not, whether cooling systems are active or not, and generate reports based on those inputs and outputs from the system that can then state whether there's a fault in the operation of that system, whether economizer is not working properly and bringing in too much outside air, or not preventing ventilation air from coming into the building. You can have dampers fail open or fail closed. Some examples of economizer compliance. For smaller systems, you can have any. I'm getting a couple of reports that I'm too quiet. Let me see if I can do something about my audio. Is that any better for everyone? Okay, I'm getting one message that is better. Okay. We'll try to carry on here. Some examples of ways to comply with fault detection and diagnostics. If you've got a smaller system that's controlled by a programmable thermostat, there are programmable thermostats that have fault detection screens built into them, so they can be linked up to controls on a furnace or small RTU. And you can see an example here on the right side of the screen. When a fault comes up, it changes the color of the screen and displays that there is an economizer fault. Another way to do this is to, with the building's BAS system, program in alarms that will generate a notification that goes to the central control system that notifies the operator that there is an economizer fault. You can see an example here on the left of a trend log where they did some analysis and found that when outside air was cool enough to provide full cooling to the building, the cooling valve was still coming on and shouldn't have been. And so they knew to go investigate for some kind of damper control issue or maybe a control issue with the cooling valve itself. So just a couple of different ways that you can get compliance with economizer fault detection and diagnostics. With language changes in the 2018 IECC that make most controls have to be configured and operable when the building is turned over to the building owner now. So you got thermostat deadbands, setback temperatures, resets for hydronic temperatures and discharge temperatures from units, economizing, demand control, ventilation. There's a lot of controls built into the IECC now to maximize energy efficiency of buildings and operational efficiency of buildings. However, if some component of that isn't tested and is installed not working properly, it can lead to a lot of issues downstream. And what we find with a lot of projects is, since commissioning is done at the end of the project, timelines get short, budgets get short, commissioning either gets removed from the project or done in a quick manner and not complete. I've actually seen, in my experience, I worked in Kentucky. We had a building that was turned over to the control group, and they had to do internal commissioning after it was turned over to them instead of a commissioning agent do it. And they had a lot of issues with that building. So commissioning is very important, and it prevents a lot of long-term comfort issues, a lot of headache for maintenance and operators when the building's turned over. Just some quick notes. Commissioning costs, we did a little bit of research. AC AAA listed, depending on building size and system types, commissioning costs anywhere from 25 cents to $1.25 per square foot. Lawrence Berkeley Laboratory reported around 18 cents per square foot per year in energy savings for doing proper commissioning at the outset of your building at a cost of about $1.16 per square foot. So this pays back within a few years. It pays for itself relatively quickly. It also is going to improve your building durability, prolong the service life of your equipment, reduce comfort complaints from the occupants, reduce callbacks to contractors from the building owners. One example we had a school district that had HVAC fans set up on schedules, and they would turn off at time, but at midnight they would turn back on instead of turning back on at 6 the next morning. So they had 6 hours of system operation that was not beneficial because there's no one in the building, and they were paying for all that energy use. As far as compliance for this, we've got some examples here of compliance forms. Usually in the construction documents, there will be some, in the specifications, there'll be a list of commissioning requirements and how a commissioning plan should be developed for the particular building systems. And these certificates are a means of demonstrating that compliance. Usually what we find, commissioning is done at the end of the project. And some of this documentation and materials that are sent to the building owner are sent after the building occupancy sent in, after your final inspection. And so these are documenting that the building owner is aware they're going to be receiving this documentation, and that they should be looking for that from their contractors. And it's also signing off that a registered design professional or a commissioning agency is taking responsibility for ensuring that commissioning is completed. So that's a couple of examples of different compliance certificates that we've seen and different methods of achieving that compliance for code officials. For shutoff dampers, anywhere you've got ventilation controls in the building, outdoor air intake or exhaust, the IECC specifies specific leakage rates for those. Those dampers should have Class 1 motorized dampers to shut off and ensure they are sealed and achieve their leakage rates. And usually what we find is most of these dampers have a tag on them that specifies they've been tested and will meet the code. But the issue is that installation issues happen and they don't achieve their leakage requirements or their design leakage rates. Most dampers will have in their installation documentation this torque data table, and there is a at the far right of this table the ceiling torque for those dampers. Whatever actuator geometry you set up and actuators you install on these dampers, in order to achieve that air tightness level for those dampers, they have to meet this close-off torque. And what we found in some cases is that geometry is not set up right, and these dampers either don't have full range of motion or just can't seal off as tightly as they should to meet their leakage requirements. So it's an important part of commissioning to make sure that dampers have that full range of motion and that they are achieving those sealant rates to ensure that they're not going to leak. For duct and plenum insulation, code specifies for supply and return ducts and plenums shall not be insulated to less than R6 where located in unconditioned space, and if outside the building should be R12. Ducts, air handlers, filter boxes should all be sealed. Unlike residential buildings, commercial buildings do not require pressure testing of ductwork, although we highly encourage it. We do realize that they are much larger buildings. It's much more difficult and much more expensive to get that testing done. But an example here in this thermal image is one of the issues we see with commercial duct insulation. This is a flange joint that has a gasket on it, but it's been affixed to the exterior insulation wrap instead of to the hard duct surface. And over time, As air pressure has moved through that duct, that sealant has pulled away from the insulation wrap, and now you've got a duct leak. And especially in semi-conditioned and unconditioned spaces, that air leakage can result in condensation, which then drips down onto ceiling tiles, and you've got a kind of a false roof leak there, and can result in callbacks. So very important to make sure that ductwork is sealed up properly. It ensures that distribution air gets to where it's supposed to be. It helps with balancing the system out as well. Some examples here: gasketed joints are fairly common in certain sections of the ductwork, but most of the joints out in the distribution system are ungasketed. They are pressure fit joints or crimped together joints. The primary concern here is where you've got tight bends or T's in the ductwork, because that's where you've got a significant pressure change. So those are the joints that are of primary concern for sealing. Again, we like to stress here, please don't use duct tape to seal ductwork together. You can see an example on the bottom left there of a duct sealant that just, they use duct tape to hold those ducts together. As the adhesive dries out, it turns into powder, and the ductwork came apart. You can see on the bottom right there, proper application of those gasketed joints. Insulation's been cut away from the duct surface so that that gasket can seal down to the internal duct liner. And that way that ensures a tight and airtight fit there. Moving on to demand control ventilation. DCVs have been provided for spaces larger than 500 square feet, with an average occupant load of 25 people or greater per 1,000 square foot of floor area, and served by systems with airside economizer, modulating damper controls for outside air, and or outside air requirement greater than 3,000 CFM. Exceptions: systems with full energy recovery complying with the energy recovery section we covered earlier, multi-zone systems without direct digital controls that can then modulate those zone airflows. So if you've got manual control or non-centralized controls of spaces, this demand control ventilation isn't necessary, mostly because it's hard to tie those systems together and get them to work properly and balance airflows. Systems with design outdoor airflow less than 1,200 CFM, spaces where supply airflow rate minus any makeup air or outgoing transfer air is less than 1,200 CFM, again, just looking at total ventilation air to that space, and where ventilation is provided only for process loads and not for occupant purposes. You can see in our image there on the right side of the screen, the large yellow box is fixed ventilation. You can see there's a lot of energy consumption there, but there are various means of achieving demand control ventilation. The most common is using CO2 sensors, mostly because it's a quick and easy way to do it. And other sources of occupant determination for spaces aren't as generally applicable. So you can see a regular schedule is included there, ticket counting, usually for theaters, large stadiums, things like that. But CO2 is most generally applicable and has the best overall energy savings. We do have a question about, do ducts within return air plenum ceilings require insulation? That is a semi-conditioned, unconditioned space. Since it's conditioned by return air coming out from below your drop ceiling or below your plenum area, those do require the R6 insulation. Exposed ductwork within the space, since it's in the conditioned zone of the building, does not require insulation. But I do like to mention that I have seen in the past, especially if the ductwork's not sealed properly, and you've got cold air leaks along that ductwork, that you can still get condensation on exposed interior ductwork. So I do like to see some minimal insulation, but it's not required. Moving back to our demand control ventilation, some common issues that we see: the economizer is not set up to override the demand control ventilation system. So DCV is saying, I don't need outside air, but you can get free cooling with the outside air, and the economizer gets locked out. So the economizer should be able to override DCV and provide free cooling when it's available. There's also confusion sometimes on CO2 set points for buildings. CO2 is used as a tracer gas to determine occupancy in spaces. It's not necessarily something that we're trying to control for in the building. So when you install a CO2 sensor, the design for demand controlled ventilation is to maintain a 700 part per million offset from ambient CO2 levels. There are two different ways to set up CO2 sensors in control systems. They can be set up with a differential set point, in which case that set point would be the 700 parts per million, measured against an outside air CO2 sensor. More common is a fixed CO2 set point, and usually we see that fixed set point somewhere around 1100 parts per million to 1200 parts per million, and that's based on an ambient CO2 level of between 400 and 500 parts per million. What we do see is, especially in heavily populated city centers, those ambient CO2 levels can get higher than that. They can get up to 600 to 800 parts per million. And if you've got a fixed CO2 set point, that can result in overventilation in the building. So just some considerations there for those CO2 set points. Be aware of what the ambient conditions for CO2 are around your building when you're setting a fixed set point for CO2 controls. Something else that we've seen on occasion is if your CO2 sensor is calling for more ventilation air and your outdoor air dampers are thrown open when it's really cold outside, that can cause freeze stats to trip. So it's a good idea to have an upper limit freeze protection set point for your ventilation. That way you're not going to trip systems out, have kind of a false maintenance issue there. And you can see kind of an example of that on the chart on the right there. There's an upper limit setting for that outside air ventilation. So for protection of piping insulation, usually we don't see this as an issue on large chilled water lines or steam lines or hot water lines that happen to run through unconditioned or outside the building. We tend to see this as an issue on small refrigeration lines for VRF systems and split systems. Usually they're wrapped with this foam wrap, and that foam wrap has a rubberized adhesive that seals the ends together, but at tight angle joints, that sealant pulls apart and exposes that foam, exposes the inside refrigeration line. And also that material is susceptible to UV degradation over time. After a couple of years, it starts to turn into a brittle material, and if you rub against it, it will turn into a powder and just flake away. You can see on the far right side screen here that white coating on the outside of that foam line. That is the UV protective coating. If that is used as your protective coating, you need to make sure that the building owner knows that as a preventative maintenance measure, that needs to be reapplied every few years based on the manufacturer's standard. Another common thing we see is supporting brackets. Often the insulation is cut away from the refrigeration line so that the line is bracketed directly. Usually that's to prevent vibration of the line and hold it more securely in place. But that removes that insulation from that area. We also see a lot of zip tying that crimps that insulation and reduces its R value. So some examples of good insulation job: mitered joints to prevent stresses on that wrap that will split that ceiling seam open. In the middle here, you've got supports that bracket around the insulation so it's not crimped or cut away. And there are UV protective wraps available for those foam insulations. You can see a couple of examples here. The Energy Code does state that that wrap cannot be an adhesive tape. So you can see that pipe wrap tape there at the bottom is actually not allowed per the IECC. It has to be a removable material that can be reinstalled after so that you can do maintenance on those lines. Say a leak springs up, you can access that area, seal that joint, and then put the insulation back in place and recover it with your protective wrap. So it is important to note that that protective outer coating does need to be a removable item for maintenance purposes. Some of the impact that poor insulation can have on that refrigeration piping. We pulled this study from the Wisconsin Energy Institute, looking specifically at the 8-inch pipe size there. So this is more like a chilled water line or a large hot water line. an annual cost per 100 foot of $36 for a properly lined system, an insulated system, increases to $120 if it's not insulated properly. So there is a significant energy cost impact to your clients to fail to insulate that piping properly. Also, that insulation provides some corrosion protection to the piping inside. So for long-term life of that piping, that insulation is important as well. Moving on to circulation systems and demand control recirculation systems. These are referring to requirements for domestic hot water systems in buildings. If one of these is installed, it is mandatory that this must be complied with. So for circulation systems, the pump shall start based on identification of demand, and that's the key point for both of these, is that they have a demand component. For the demand recirculation, that's referring to lines that are recirculating hot water back to a common cold return line. That has an additional requirement that that cold water piping should limit that return temperature to 104 degrees Fahrenheit. But the key thing here is that you cannot have, per the IECC code, a continuously running hot water circulation system. These are just a couple of different examples. You've got the hot water return dedicated loop on the left of the screen, and you've got the demand recirculation with a common cold return on the right side of the screen. We do get a lot of questions about health code compliance and whether Legionella and Legionnaire's disease is a concern with these systems. Usually what we find in most of the research that we've looked at is that these circulation pumps are going to cycle enough with demand to prevent buildup and of any kind of material in your piping that's going to allow growth of Legionella's disease. And so the general consensus at the moment is that this does not create an additional hazard. However, if you do have a building for at-risk populations, such as hospitals or elderly centers, you may be able to get an exemption for this based on health and safety. But again, the general consensus is for a regularly occupied building with regular hot water demands, these are going to cycle enough to keep the system at temperature and to keep flow rates through the system to prevent stagnation. Another key component is proper design of the system to prevent dead legs and prevent low flow areas where you would get buildup inside the piping that would allow the growth of microbes. For freeze protection systems, they must have some kind of control that turns off the freeze protection system when there's no risk of freezing to the protected fluid. It's very common for us to see heat trace piping. That heat trace continuously draws wattage even when freezing is not a risk. You can see here at a pipe temperature of 40 degrees, you're still pulling about 3 watts per foot for this particular heat trace. So even though it's self-regulating, it doesn't shut off when there's no risk of freezing. It's still pulling some power. So the Energy Code has built-in language that those things have to have some kind of automated shut-off when there's no risk of freeze. For air handlers, one of the things we see for freeze protection of chilled water coils is a freeze protection recirculation pump. These are plumbed in parallel with the coil. You can see on the top image here. That pump should only come on for freeze protection of that coil when the freeze stat on the air handler trips. We often see these confused with booster pumps, which would be plumbed in series, usually on the supply or return side. Those types of pumps are installed to maintain turbulent flow through the coil, to maintain a stable performance for that coil. If flows drop off low enough to get to laminar flow, then you get a sudden decrease in that coil's performance. But these pumps that are plumbed in parallel are specifically for freeze protection and should only run for that purpose. Another thing to consider for cooling towers that are going to run in the wintertime, typically seen on data centers and places with high internal heat loads, those cooling towers, that freeze protection setting should be based on the wet bulb temperature and not dry bulb outside temperature for fluids going through the fill of that tower. The reason being, even on a day when it's 40 degrees out, if your wet bulb temperature is below freezing, you can still evaporate water out of that fill and drop that temperature down to a point where that water will freeze, that will expand in the fill and damage it. So for cooling towers, specifically the fill section, wet bulb temperature sensor should be used for freeze protection. Other components like the sump, external piping lines and stuff can use a dry bulb sensor. That wraps up our HVAC section. Before we move on to the residential requirements, we have a couple of poll questions just to check how we did and check your comprehension on some of these measures. I'm going to launch that poll now. The first question is, for a building with an 8-ton cooling system requirement, which system would not be allowed to be installed? There are 4 options there. Keep in mind that you are allowed to have a backup system, standby. You're allowed to have systems that can modulate to meet the load in the building. So go ahead and start answering those questions. The second question is, which is not an exception for the requirement for demand controlled ventilation? So there are a few options there: full energy recovery, just heat recovery, multi-zone systems. And if there are any questions about anything that we've covered while people are answering this poll, feel free to enter those in the question and answer section, and we'll try to get to those in a brief pause here. All right, we're getting some answers coming in here. Okay, give it a few more seconds here and then we'll close the poll. Looks like the first question, a lot of people are agreeing on the answer. Second question, we've got a little bit of a spread. Okay, we'll give it another 10 seconds here and then we'll end the poll. All right, so for question 1, looks like most people got that one correct. The 10-ton constant speed system doesn't have the ability to modulate. It's oversized for that 8-ton cooling. That would not be the applicable, that would not be in compliance. For question number 2, looks like I did not cover that one well enough. For demand control ventilation, systems with heat recovery are not accepted from having demand control ventilation. Full heat recovery is an exception. Multi-zone systems without direct digital controls. Again, I noted in that section there that that main purpose there is to prevent unbalancing the system if you've got individually controlled zones that aren't by a direct digital control centralized system. The other 2 requirements there are both based on outside airflow rate. If you're less than that 1200 CFM of ventilation air coming in the space, then you do not need to have demand controlled ventilation for that space. So the correct answer there was systems with just heat recovery. That would have been the correct answer. So we'll try to cover that better in the future. I will now hand it over to Ryan to cover the requirements for the residential provisions.
Well, thank you, Sean. So these are the 10 that we're going to go through here, listed on the front end. With that, starting from the certificate, now keeping in mind Illinois has been on the energy code for about 10 years now, so anything built within the last 10 years should already have this. So This is required to be permanently posted, typically either where the furnace is, utility room, or an approved location. The other location that we typically find this in, if it's not by the furnace, is normally with the electrical panel, uh, either on the outside of the cover, uh, such that when you open the cover, we've not obstructed the visibility of the other required labels, such as the labeled of the circuit schedule. So the code does call out several requirements that the certificate needs to include. And so here's some examples of what that might look like. There's several different formats that this can be in, and it is kind of up to the design professionals and their preference as to what it might look like. But the code does call out what parameters it needs to include. Uh, some of the importance behind this is understanding if something in the building changed since the original design. One example of this might be if I have an attic here, it says it was an R38 originally, but if I look in the attic and I find R60 up there, I know that the building has been improved from original design, which may impact future the requirements for heating and air system. So if I go to replace a heating and air system and I see that my insulation has been improved, uh, then I may be able to actually decrease the sizing of that unit. Uh, Similarly, windows and their U factor. So in case I break a window, uh, because the label that normally tells me how good that window is long since been lost, uh, this provides some information as far as if I break a window, what the U value of the replacement needs to be. So with that, now this is a little bit older. You'll notice this is a 2012 certificate. I would be very skeptical if I received this certificate on the left, because these are exactly the minimum values stated by the code at that time. So the likelihood that I had a blower door that had exactly a 3 air changes per hour and the duct testing came in at exactly 4 CFM per 100 square foot, I would be skeptical of the results of this. Not saying that's not possible, but if everything is exactly code minimum, that's a little suspicious. So as far as insulation, I know this is a prescriptive requirement. We call this out because there is an Illinois amendment on this, such that the entire state is on the same value for the basement walls. And also noting that if we have a heated slab on grade, then we need an additional R5 insulation under the slab as well as added to the outer edge of the slab. And the importance there is we want to make sure that there's a thermal break between the slab and the ground that it would be in contact with, so that we are pushing heat into the house rather than from the slab into the ground. Now, this table here, table R402.4.1.1, this is a very critical table. Most errors that we find causing indoor air quality issues and the like, mold issues and similar things, typically you'll find the error on this table. This talks about insulation installation as well as air barriers. And so something we like to call out here is this first one in the general requirements for insulation installation, and that is not to use air permeable insulation as an air sealing material. So, fibrous insulation is not an air barrier, and so we need to make sure that we use a separate air barrier from that. So insulation installation quality really matters. Fortunately, the home energy rating system has provided grades of insulation as far as how good was it. because improper installation can really have a dramatic impact on that. So they call out grade 1 as the best, and that is where everything has been completely filled and not compressed. So this is a perfect insulation job, whereas grade 3, being the lowest grade, is when you have somewhere between uh, 2 and 5% errors. So that can be very critical, that the difference between the best and the worst is only 5%. So just being aware that getting those uh, details is key. So making sure that we've filled the cavity all the way, uh, and that we've a common error that we will see is for floor insulation, where the insulation is not fully in contact with the floor above, uh, or compressed around wires, not cut neatly around boxes. So making sure, again, all these little details add up. So for basement walls, this is noting there is a slash rating in that table. So a 10/13 means I'm using either an R10 continuous insulation, either on the interior or the exterior of that wall, or I'm using an R13 cavity insulation on the interior of the wall. The code calls out that that needs to go down to 10 foot below grade or the bottom of the floor, whichever is less. Illinois does allow you to stop that 6 inches before reaching the bottom of the floor. But it also provides, if you go with a higher insulation value of 15/19, that you can stop that after only 4 foot below grade, rather than having to go down 10 foot below grade. So a little bit, providing a little bit of a trade-off there. You can go to a higher insulation value, but not have to go as deep with that. So air leakage being mandatory. This is something it's been coming for a little bit of time here, and we have seen improved compliance with this. Uh, Air sealing is one of the biggest changes that we have seen in the residential energy code, and that was one of the biggest driving factors during one of the more recent changes, was reducing that air infiltration allowance. So uh, when we're doing this, we first need to identify where the thermal envelope is, because the thermal barrier and the air barrier need to be in intimate contact with each other. So once we know where the thermal envelope is, here we have 3 examples that are the same footprint of a building, but the thermal envelope is very different in these. So once we know where the thermal envelope and the air barrier should be, now we know where we need to make sure we've gone through and done our critical sealing of these areas. So uh, uh, talk a little bit more about some of these common areas a little bit later. But first we have to, for air leakage, we have to install it properly, then we have to test it. In the commercial side, there is not a requirement at this time to test it, but you still need to do your air sealing. So here in the state of Illinois, there is presently an Illinois amendment on this, such that the air leakage rate cannot exceed 4 air changes per hour at a pressure of 50 pascals here in the state of Illinois. If you look in the International Energy Conservation Code for the state of Illinois, it would list an air leakage requirement of 3 air changes per hour. So here we are back at that table R402, and here we're looking at the air barrier. And so noting here, again, we want to make sure that air barrier is continuous, and that wherever you have joints between materials, that we have some methodology to seal those back together. Rarely do you find problems with air sealing in the large flat open spaces. Normally it will be at corners, joints, and where two dissimilar materials come together. So uh, the U.S. Department of Energy has put out an air leakage guide, and while we do appreciate paying less on our heating bills, uh, really air leakage is going to come down to comfort improvements too. Also, by reducing the air leakage into and out of through the envelope, that is also reducing our likelihood of creating mold, because air leaking through that envelope is likely to be carrying moisture through that. So there's many different ways to seal house, either through weather stripping, sweeps, caulks, gaskets, and the like. There's many different examples. There's now new sprayed in products, foam products, caulking, so many different ways to accomplish that. Some of the more common areas that we find problematic or problems in sealing, particularly in the upper right-hand corner there, you see a soffit commonly found in kitchens with the little can light over the sink. Those soffits typically are not sealed properly uh, and open through to the attic. Uh, so many different locations that you'll have problems. Uh, and here we see why the details, you need to get them right. In the upper left there is an attic hatch that is insulated. They'd even gone through the effort to put the thumb locks on that and really help trying to do the right thing there. Unfortunately, they had forgotten one little detail, and that is they had forgotten to put a little weather strip in to provide that good seal. So as air leaked by that attic access, the moisture condensed on that panel inside and then caused mold, or the mold grew there. So a lot of things, again, going back to those details mattering. So next up is blower door testing. So here noting again this 4 air changes per hour. The code official may require this to be done by a third party. Noting this is an approved third party, approved being acceptable to the code official. So this is not uncommon to have it done by a third party. You normally would not necessarily want the builder of the building to do the test and show that, because of the direct conflict of interest. So, and the important thing here is to make sure that all the penetrations in the building thermal envelope have been made. So that could be exhaust fans, any ductwork for dryer vents, HVAC penetrations, and the like. So it does call out in the code several aspects as far as how to carry out this procedure, and noting what do you close but not seal, and then other areas where you can actually tape it off and seal it. So if you're working in multifamily housing, for low-rise multifamily, there is an Illinois amendment to allow you to use a surface area metric rather than a volumetric measurement for the blower door testing. And the reason being is when you get into smaller units, the volume to surface area ratio ends up skewing and being much harder to pass. Using this surface area method is actually a much more accurate method. So noting here, we're going to add up all the surface area of the outside of the enclosure on all 6 sides. So top, bottom, and the 4 sides, or more if there's, in this case, there might be jut outs that you might need to add on too. And then multiplying that surface area by 0.25, and that is your limit for testing on that. Now, if you do have a very large installation, such as the one here, if you have more than 7 units in a single development, then a sampling protocol may be available to you as well. Again, you'll find this in the Illinois amendments to the code. So once we've gotten through the envelope, now into the ducts. So we need to make sure that we insulate them. And here noting that attics require a little bit higher duct insulation than other unconditioned locations. And there is an exception where you don't necessarily have to insulate the ducts if they're located completely inside the thermal envelope. Now you may still choose to insulate them for other purposes such as prevention of condensation, but they're not required by the code to do that. So once we've insulated them, next up is we need to make sure that we have sealed the ducts. Preferably you will seal the ducts before you insulate them because you need to make sure that you've sealed them either with an approved UL tape or a duct mastic. So, and you know, the important reason here is we need to make sure that the air that leaves the furnace and air conditioner actually reaches the spaces that they were intended for. If you end up with supply duct leaking out a bunch of air before it reaches the end of the run, you know, the end of that run, whatever that is, frequently a bedroom, doesn't receive enough air and causes comfort issues. So again, noting here, either a duct or a mastic or a tape or a mastic, and noting this should be a UL approved tape and not just a standard foil tape. That UL tape tends to be a little bit thicker and more durable than the typical foil tape you might just see on the shelf. So, once we have sealed the ducts, then we make sure we test them. So we can either do this before or after the air handler is installed. If the air handler has not yet been installed, this will likely require 2 tests, one of the supply air and one of the return ducts, and then you add those numbers together for your total duct leakage. So if the air handler is installed, the limit is a little bit higher. Also, it allows you to do it in a single test. So this is showing some of the steps to that, sealing it off, and then pressurizing this duct. Frequently in older buildings, we had seen building cavities been used as ductwork. This is no longer allowed. You may put ductwork within framing cavities, but the cavity itself cannot be the ductwork. On the left-hand side there, you can see that was a return used as the building cavity. The problem is, as you see in the thermal image, we are actually pulling hot attic air into that building cavity, which is going to reduce the effectiveness and cause comfort issues. So, pipe insulation. Normally on the hot water side, this is typically done correctly. On the mechanical side, the challenge here is both the hot and the cold lines should be insulated because the hot line can be carrying greater than 105-degree refrigerant, and so that also needs to be insulated. And similar to the commercial, need to protect it from weather and sunlight. So very similar requirements there. As far as where you have to insulate hot water pipes, when you get into 3/4 inch and larger, or several other things such as where piping may leave the conditioned space, or if you're serving more than one dwelling unit. So, heating and air equipment load sizing, this is another mandatory requirement. Hopefully no one has seen this been used, but in older times, we might have seen this been used. We love the directions on this. To stand on the curb across the street and hold this page 1 foot from your face, and then find the hole that most closely matches. Across the street is not a defined measurement. And so you can end up with a lot of inaccuracies of this. Also, it doesn't take into account how deep the house is. So we now have to do a manual J load calculation or other approved load calculation. Again, noting that approved is acceptable to the code official. Fortunately, the manual J, it's not terribly difficult to go through. Even the online tutorial by the ACCA is about 30 minutes. So even the tutorial is only about a half hour. Probably the thing that takes the longest is just finding what the windows and doors and walls are as far as the values in the manual. So here we call out that the manual J and then manual S are required by the code. ACCA also does have a manual D, which is for duct sizing. That can be very beneficial, and even though it's not called for in the code as a required practice, going through and doing a manual D will allow you to install ducts that are adequately sized to deliver the air to the locations desired, so that you don't have to, likely to reduce a callback of a comfort issue by going through and doing the manual D, even though it's not required by the code. So obviously our buildings have gotten much better. We've improved our thermal envelope. We've added more insulation. We also have dramatically improved the air tightness, noting now the code is calling for around a 4 air changes per hour or less. In previous construction, it was not uncommon to see air changes at 50 pascals of 10 or even 20. So we've also dramatically reduced the loads that we are placing on these buildings. So with that, we've reduced our loads and reduced the air infiltration. So with that, we need to make sure that we are sizing correctly. Something we do call out here is in the manual J, one of the inputs is what is your design condition for cooling and heating. I'll note that here on the cooling side, this is published by ASHRAE. Not a single one of these values is 100 degrees or more. This is not saying what is the highest temperature the building might see, but this is looking at what is the temperature that the building will see no higher than 1% of the year. So most of these here you can see across the state of Illinois, somewhere around upper 80s to low 90s. So if someone receives a manual J calculation and it states the outdoor condition for the summer is 100 degrees, then you need to send that back as it was not done correctly. That is one easy check for a manual J. So now that we've made our homes tighter, we now have to make sure that we ventilate them. Build it tight and ventilate right is something that I've been told. And what this allows us to do is bring in outdoor air on our terms and in the quantities that we desire, no matter the weather conditions outside. Previously, when we relied on air infiltration, that was great on days that were windy, but on still days, then you weren't getting your ventilation that you needed. I personally prefer to breathe on all days, not just on windy days. So installing mechanical ventilation is very important to modern construction. So there are 3 types of ventilation: negative, positive, and balanced, also called exhaust only, supply only, and balanced. So the International Residential Code does have, as far as what the requirements are for this ventilation airflow, and it either requires these systems to operate continuously or they may operate intermittently but they must operate for at least 25% in every 4-hour window. So in this example, if I have a 4 to 5 bedroom dwelling unit that is less than 1,500 square foot, by the table I need 60 cubic feet of air per minute from outdoor air. So if I use a fan that is sized for 240 CFM, I could operate that fan 1 hour out of every 4. So what this says is if you are using an intermittent fan, the minimum number of times it will start in a day is going to have to be no less than uh, 6 times, because it will have to start every 4 hours. So here's a pictorial description as far as what negative, positive, and balanced looks like. Negative ventilation or exhaust only, this is probably what we see the most common. However, this is the least desirable method because we are relying on air to leak in from the outside. Outside air here in the Illinois, particularly in the summertime, is going to be very humid. And so we have a potential of causing dew point to be inside that wall cavity. So these will normally use fairly small fans located in a central location, a stairway or hallway that operates either continuously or near continuously. Supply only or positive ventilation. Uh, Typically, you'll see this on the return of the heating and air unit. So this is a little bit better because now we're leaking air from inside that we have conditioned to the outside. But again, in the winter, if you have a humidifier particularly, you can cause condensation to form in that wall cavity again, leading to mold issues. So balanced, this could either be done through a heating or energy recovery ventilation system, or it may be done using both a combination of positive and negative at the same time. So having a fan bring air in and a fan exhausting air out. This maintains the pressure boundary so that you're not driving air either into or out of the building, but making sure that we've balanced it. One benefit of doing this is where you have the two air streams, you can exchange that heating and or energy. So if you use an energy recovery ventilator in the winter, you can help keep that moisture inside the home. So in the winter, you won't get that very dry air as badly. So probably the least common that we see, but the most effective. So Illinois has made several amendments to the Illinois Energy Conservation Code. Most of these are pulling tables and values from the International Residential Code, understanding that not every jurisdiction has adopted current versions of a residential code. We've seen some jurisdictions, their codes even are adopted back to the 1970s. So by having these Illinois amendments, it helps pull the modern requirements in to the building codes that would be corresponding with the energy code. As far as lighting, so there is an Illinois amendment here for the lighting, defining high efficacy lamps. Here noting that it's 65 lumens per watt for a lamp and at least 55 lumens per watt for a fixture. When we did a market basket analysis of this, of the 400 products that we looked at, 85% of them were achieved this level, and most of the ones that did not achieve this level tended to be the more expensive ones. So these are very commonly available and not very difficult to achieve. The limit as far as how much you need has been raised to 90%. Previously, it had to be at least 75% of the fixtures. Another important change for the 2018 version is the low voltage exception was removed. So you count every fixture in the home and not just the ones that are line voltage or 120 volts. So for those lights that may be in the building thermal envelope, making sure that they are sealed and either gasketed or through a caulking or other sealing method, and they need to be listed as airtight. So they'll be labeled clearly. All right, additions and alterations. This is where we get into a lot of our questions come for alterations of buildings. So here noting that we cannot reduce the compliance of a building by making an alteration. So the alteration has to maintain the compliance with the code, and it can't make it any worse. So also it does note that any alterations need to be made such that they comply with the provisions of the current code. However, it does not require that unaltered portions be brought up to the code. So in this case, here I have a basement. If the lighting was already existing and I'm going to be modifying this wall, then I need to make sure that I bring that wall up to the current standard. Modification being I'm going to build a new exterior wall. So the exterior walls might have to be brought up to the current standard, but the heating and air system would not necessarily have to be altered to meet the current code. There are a few exceptions. One of the more common ones that we get with, as far as roofs. So a few things with that is, as far as if you have construction and you expose a roof, wall, or floor cavity, then you need to fill that cavity with insulation. And also if you're doing a roof recover, we note here this is to check the definition, a roof recover is where you place a new weather-resisting membrane over top of the existing. So you keep the existing membrane in place, and then you place a new membrane over the top of that. That is not required to be brought up to the current standard. So here's some pictures of that. You'll see in the lower left, an attic where a cavity was exposed, and so he's going ahead and insulating that cavity. It does not require that cavity to be furred out to provide the full insulation value, such as an R20 for a wall in the exterior. However, the cavity needs to be filled. The lower right there, you can see this was perhaps an old masonry building with furring strips. There doesn't have a cavity, so no cavity was exposed when the plaster was removed. Insulation would not be required to go back. So Illinois has added an amendment for a roof membrane peel and replacement. We do note that this is not likely to apply as flat roofs or low slope roofs are rarely replaced before there's ever a leak. If you have a leak, you now have damaged roof insulation and potentially a damaged substrate, which need to be repaired before a new membrane goes on. What this is you remove the existing membrane alone and place a new membrane in its place, and that is it. So if you have to do insulation work or repairs to the roof deck, then this does not qualify as a peel and replace. So, however, noting that one challenge that common occurrence here for low slope roofs would be I don't have the ability to get to the full R30. And here noting that they need to comply without requiring unaltered portions to be modified. So in this case here, see I have a parapet wall. If I need 5 inches of insulation to achieve my R30, I presently have 1. And my flashing detail goes up where I only have 1 course, or I could raise that flashing detail by 3 inches. So what this is calling out for is I need to add the 3 inches I have room for, and that is it, because alterations shall not create an unsafe or hazardous condition or overload the existing systems. If I tried to put in more than the 3 additional inches, I would not be able to provide proper flashing, which could damage the building in the long term. So, with that, I believe we have another poll question, another couple of poll questions here that Sean will launch. So, the first one asking about how I can avoid having to test ductwork with a couple of different answers there. The second one being, if I need to repair or replace insulation or roof decking, can I still qualify under the peel and replacement under the Illinois amendments? Yes, no, or if I can sneak it by the inspector. So, did have a question come in as far as the slides. A copy of the slides of today's presentation will be posted here before long to our website. Again, sedac.org/energy-code. So you will be able to get copies of that after the presentation. Or if you need something else, again, feel free to go ahead and email us, energycode@sedac.org. So if anyone else does have some questions, go ahead and place them into the question and answer section.
We did get a comment on the residential certificate. It is true that is only required for new construction. Although, if you've got a renovation or alteration to a building, it might be helpful to the building owner to go ahead and give them that certificate for future reference purposes.
And that is something that, while the code may require something, yes, as Sean notes, generating that, even if you're only able to generate part of it, it may be something that you go ahead and generate a blank certificate and fill in whatever you know, and provide that to the building owner. That can be very helpful to them. So, question here about Illinois, or the historic building exceptions. There is an exception for the Illinois Energy Code for buildings that are listed on the Illinois or National Historic Registers, and also for buildings that are designed by or designated by the authorized personnel, typically going to be either your code official or your historic preservation agency, as historically significant. So if your building is not listed as on the national or state register, the International Energy Conservation Code also has a provision to allow you to exempt certain specific work from the code that would be for specific historic details where compliance would damage those details. So something such as, insulating a wall is not likely to damage the historic character of a building. However, in the part 1 of this series, on the commercial sector, Sean had noted one of the buildings that had a beautiful historic Tiffany's dome. That historic dome could be protected even if you're updating, even if the rest of the room might not be exempt. So let's go ahead and share our results here. Avoiding, how do I avoid having to test the ductwork? Most everyone got this, that yes, we need to locate the ductwork and the air handler inside the thermal envelope. Now, if the air handler is outside of the thermal envelope, I still have to test the ductwork. So good one there. And then if I need to repair or replace the insulation and roof decking, can I qualify under peel and replacement? Most everyone got this one as well, but it's split here. No, if you do need to do insulation or roof decking work, then you are no longer under peel and replacement, and you do have to bring the code, the low slope roof, up to the current standard to the best of your ability within the existing condition constraints, such as parapet walls, HVAC equipment curbs, and the like. So I think there's another poll here as far as the duration here that Sean will launch. So
all right, we've had a few more questions come into the Q&A. The first one, any thoughts on R versus U values to calc out insulation ratings? R values are prescriptive, so that's denoting if you're going to follow the R value method, you have to put in that R value in a cavity or in your continuous insulation. The U values give you a lot more flexibility because it considers the whole assembly. If you're looking for some flexibility to get a slightly less insulation, usually the U factor method is the way to achieve that.
another benefit from doing the U value, or there's a benefit and also something to watch out for. One benefit is it allows you to trade between continuous and cavity insulation, so that you can actually provide all your insulation through continuous insulation and not have to do any cavity insulation. This could be beneficial if you're going to do an exterior continuous insulation. However, if you trade in the other direction and only put cavity insulation, something to be aware of is that can cause you some energy, comfort, and mold issues, particularly a little less common in the residential side, but particularly if you're using metal studs, that thermal conductivity really gives you a big penalty on that. So yeah, as Sean notes, the U value does give you a little more flexibility, and it's commonly people will use that to want to trade away requiring continuous insulation and use just cavity insulation, but it can be traded so that all you need is continuous and can skip the cavity altogether, which, if you do that, also makes those cavities much easier for the electricians and plumbers to use, plus will likely prevent any potential of frozen pipes, because then all the pipes would be on the inside of the thermal envelope.
Okay, next question was, can we share some common, free, or easy to use energy modeling software programs for residential architects? And can we offer some training on those? The most common modeling program, it's not free, but it's REMRate. It's used by HERS raters to do their rating process. I'm not aware of any other commonly used rating programs or modeling programs for residential, although eQuest is a little overkill for residential, but it can be used for that purpose, and it is a free software. But it's definitely more difficult in use than REMRate. REMRate just requires inputs for insulation, HVAC equipment, some, whether you specified Energy Star appliances or not. So it has a pretty easy to walk through interface. Whether we can offer some training on using those, we can look into that in the future. We actually do have, there is a performance modeling path for ResCheck, and we will be walking through that when we do our ResCheck presentation on May 6th.
Question here about if there's any requirements for exterior lighting as far as lumens per watt or efficacy. I believe that the 90% of fixtures is just for, actually that 90% would appear to include exterior lighting as well as interior lighting, because it does not specify interior. So it's 90% of all fixtures need to be high efficacy.
The name of that modeling software was REMRate, capital R, capital E, capital M, rate. It's a Canadian software program that's used by most HERS raters.
Looks like we also have another potential one here out of UCLA, the HEED tool. I don't have any familiarity with that one, but that has been suggested by one of our participants here as well.
I was typing an answer to that one. Oh, well. We'll try to email you the link to that HEED software as well.
Had another question here. If we could go back and look at the insulation installation, some of these details. Here we've got some details as far as insulation that didn't run quite to the end of its cavity. Another one here where it's been compressed a little bit too much. It was not allowed to fully fill the cavity. So some of this may be compressed through either piping or wiring. And then in the lower left there, noting the proper method is to split the bat so that half the bat will go behind the wire and half will go in front of the wire. So making sure that we're cutting around the electrical boxes and making sure the insulation. Something to be aware of when you're cutting around those electrical boxes is you would not be cutting the full depth of the insulation likely unless that box is going the full depth of that cavity. So being a little bit judicious about removing just the insulation wherever the box is actually taking up for that volume. So here we can see some fairly filled cavities and then some where it's just been compressed. Commonly, if we have wire ties, that may also lead to compression, particularly in floor insulation. Slides should be uploaded here before too long. It might be a day or two. Otherwise, because this is a two-part series that's part of a larger version, you actually can go under our workshop series and download most of these slides from one of the previous workshops that we have done this current year. So again, want to thank everyone for participating today, and we're going to go ahead and send out certificates for those who participated. And then if you need your AIA or ICC credits, go ahead and reply back to that email and provide your AIA or ICC member numbers, and we'll go ahead and get those credits filed for you. So,
thank you all for attending.